Okay, then, welcome to the second lecture of DAEs. Today we will talk about basic notions from DAE calculus that we need in order to talk about what is a solution, or even starting with what is a DAE. And maybe a quick reminder, last lecture we had what is a DAE? But in more verbose terms, so this was like talking about what might be a DAE, examples and applications, and a bit of an outlook on difficulties, or why it's worth spending a whole semester on DAEs. Okay, and today we want to start with the theory on all that, and for that we need like the right words to talk about that, and that's what we're going to introduce today. We will start with how can we write a DAE in a general form, and for that let me write down just the equations, or basically the representation. Here, this is what we are going to use to describe a DAE if we don't specify anything more, like maybe particular structure, or maybe because it's linear or whatsoever. So there will be examples, but this is the most general form that we can write a DAE in. And this takes so here f is a function that takes the time from a time interval. So here that's the time interval. I have some, so here the t comes from this time interval, then it takes the solution, so to say, at time t, so it maps from the domain where the solution lives in, and also from the domain here, this is this part where the time derivative of the potential solution lives in, and maps this into the r to the m. Here we have this equation, we equal this to 0, so what the f delivers will be set to 0 in r to the m. Here we have this time interval, that's the time interval where we consider the solutions on. So this will start with, how did I write this? T0, and it has an end time, TE. Let's take the half open interval, then we can also make some sense if this is infinity. Then what we have a function x that takes this time interval and returns in vector into the r to the n. This is, can I have some more colors, please? Okay, I'll write this here. This is the time interval. This is, so to say, the solution. And then, we want to have that x dot is shall be the time derivative of the solution. So it will also take t in this time interval and return a value r to the n. And this is supposed to be the time derivative. And we say that x and x dot, or x makes a solution to this if these f apply to all this equals 0 for all t in this time interval. As we know it from ODEs, if we wanted to have, so take a better color. So like for ordinary differential equations, like for ODEs, we can only expect a unique solution if we fix the initial value. We can only expect unique solutions or well-posed problems. You can phrase it like this: Unix solutions. If we fix an initial value, and that's what we're going to do here as well. So there will often be this additional initial value, or the requirement that x of t0 should be the same as x0. And the reason why this is so separated, we don't write this into one, yeah, because initial values will play their own role in the analysis of DAEs, and that's why it makes sense to sometimes just consider the DAE, which is this equation here, and then maybe equip it with an initial value, and then talk about solutions of the DAE, and also talk about solutions of the initial value problem. But there will be a definition to that in a second. Here I now just wanted to write down an example. Maybe the easy example that we have had from before, like x1 dot of t as x2 and 0 as x2 of t minus g of t. Well, and then think of what is the f, what is the x, and so on. And well, the f we could write as, so then we will have x of t. What do we take for that? No, x maybe not so good. Let's take two vectors, u and v, that we define as, okay, well, that we define as, so this will be a vector because we have two-dimensional problem here. This will be, u1 minus u2, and here we will have, put it like that. No, that was wrong already. So this will be v1, because v we will associate with the time derivative v1 x minus u2, and minus u2 plus g of t. So this will be basically our function that takes t, u, and v, returns that, and in this case, well, then with this way we can write this as f of t x of t x dot of t is equal to 0 if we take the f in this form. Well, as you see, this is somewhat artificial, but having such a very general description of a function often can save us a lot of words. Okay, and I have it in the script. Maybe you can, or maybe I put it on the exercise sheets. Might be a good exercise to start working again in the semester. Well, trying to put the examples that we had before in this form with the f. Okay, but now we go on, and we want to talk about what can be such a solution to a DAE. Because in order to talk of a solution, we need to define what can be a solution. So of course, yeah, it should somehow fulfill the equations, but yeah, maybe there's more to that, and we will see. So this is definition 2.1, and it starts with a function. So certainly a solution should be a function, x in C1, so we want to have it continuously differentiable, taking t in this time interval and mapping into the Rn. This should be okay, so it's called a solution to the DAE. Well, this is if f of t, x of t, and x dot of t equals 0 for all t. For all t on this time interval. And no surprise. So that's what one really should expect. If we have a solution, then it should fulfill this equation. So it should have this derivative. That's why we require it to be 1 times differentiable, and then it should fulfill this and at every time point t. So this is the solution. And now it turns out why we did so much separation between the DAE and this initial value condition. Then because now a function a function x again, so again a possible candidate function r to the n is called a solution to the initial value problem. Which is now more than that. Let me highlight this a bit. For the initial value problem, and this should be, well, equation 2.1 plus 2.2. No surprise then again if furthermore, so it should be a solution to the DAE, but it should also fulfill the constraint. So if furthermore x of t0 is x0 holds. No surprise here, but now this is somewhat more. So this also holds for ordinary differential equation. Now the last point is more specific to DAEs, and because this is now about the initial condition. So an initial condition. Okay, this is really important. So it's about the initial condition. 2.2 is called consistent. Very important, so very important term, consistent for the DAE 2.1. Well, if it admits a solution. Okay, yeah. So we will have examples, and basically not difficult to construct these, where the initial condition, well, does not admit a solution, and then we say that it's inconsistent. Just think of the pendulum. If you want to start the pendulum at a position that is not on the path, then, well, you won't find a solution that is continuously differentiable. Okay, but we will talk about consistency of initial values later. First, I want to make 2 short remarks. So that x should be in C1 can be relaxed because often not all parts of X need to be differentiable. Think again of this example this example. Here you see we don't have a time derivative on the x2, so in order to make sense of these equations, we wouldn't need that x2 is continuously differentiable. Well, but in order to have most general theory, we just stay with x and c1, and if you really consider particular problems, then yeah, you might differentiate in at this point. And then consistency is a major issue, and well, this will pop up over and over in this lecture. Yeah, we will have many examples to that, and that's specific to DAEs, and it's also a very important thing. And in fact, the next chapter that we consider, the next part, is on initial conditions and whether they are consistent or not. For that, we go back to this example of the pendulum. So this was, what color are we? So this was the pendulum. Let me draw this once more for you. So we had pendulum that was fixed somewhere. Here was this rod of length L, and here is the mass m that can move either this way or this way, and those were the equations for this pendulum. And this constraint that the x coordinates and the y coordinates are always on the circle that are defined through the L, and the coordinates of the center that had to hold all the time. And now if we want to do a simulation, we of course need to start somewhere. So to use this model, we would need a starting point. That yeah, we need a starting point, and sorry, bad. Can I fit this here? It was a bit okay. So to use this model for prediction, we would need a starting point, meaning for t equal t0, we have to give the positions of this mass and as well as the velocities. You can think of, if the mass was somewhere else, you would have a different prediction. Also, if there was a different velocity at this moment, then also prediction might change a lot. So how did I write this here? Okay. All right. So we need x0 at x0 and y at t0. They should equal some x0 and y0. Okay, and we need the initial velocities. So the v at t0 and the u or t0, they should also equal some velocity v0 and u0. If we have that, then we can integrate these equations. In the exercise, it will we will see that the lambda does not need an initial condition. That's another topic. We won't go into that right now. So for now, it's important to note that we want to use this model, and so what we need is a starting point to start the simulation, and the starting point is by physical reasons, it's given through the initial position of the pendulum and through its initial velocity. It's easy to see that the initial positions, they should certainly lie on the circle. Meaning, okay. No. Okay. So this didn't work out for me. So these initial positions need to lie on the circle, meaning they obviously x0, y0 must fulfill h at t is equal to t0. What is here? This was the h of t, x of t, and y of t. Meaning these initial positions need to lie on the circle, and, or in other words, they need to fulfill this h function at t is equal to 0. Then we have, so by physical reasons, we have that h of t, x of t, y of t is 0 all time. That's a constraint. If we have a solution, then this might be 0 all time. But this also means that if we differentiate this with respect to time, so d of dth must be 0 too. So if this is a constant function in time, h is a constant function of time, which this means in particular that its time derivative will vanish. So this should be 0. And this gives us, so one can of course differentiate this h function, and this gives us that 2 of x of t minus xc times x dot of t plus 2 of y of t minus yc times y dot of t. This should be 0. And in particular, this means that we need, so at t is t0, this should hold for all time t, and this will then give that at t is equal to 0, this gives x0 minus xc x dot, so the initial condition on the velocity was the u0 plus 2 times y0 minus yc times the v0. This should be 0 as well, and this then gives a condition on the u0. So what we conclude from here, u0, y0 need to fulfill a consistency condition, too. Okay, where did I put this? The 2.4 is this equation. So here, if you want to look it up in the script, this is equation 2.4. Okay, well, this is about initial conditions and consistency. And with the example of the pendulum, it's somehow clear from physics that the velocity, the initial position should be on the circle, and then using the equations, one can derive that also the initial velocities should fulfill this condition, and one can see this is basically a geometric condition too, meaning that the vector of u0 and y0 should be perpendicular to to this vector y minus yc and x0 minus xc, and this means so a vector that is perpendicular should point in this direction. So, and this also makes physical sense that the initial velocities should be tangential to the circle. Here I just write down tangential condition. Tangential condition. Okay, and now, so much for this. Was another example why these initial conditions play a major role, and the term for that is the so-called hidden constraints, because this very condition was not obvious from these equations, and we needed to work on the equations to reveal these consistency conditions. And this happened with these time derivative of the equations, and then we arrived at this tangential condition, and this is the hidden constraint for the pendulum equations. If we now, for example, look at the circuit equation that we had two in the last lecture, then well, these are very obvious constraints that x1 and x3 should at t equal to 0 should be equal to minus u to the 0, and well, and x3 should be 0 at t0 too. So here it's pretty obvious what is the case here. What I wanted you to show here. Okay, yeah, this was the hidden constraint was referring to the pendulum, to this tangential condition. And do I go into details here? What's the time? Yeah. What did I wanted to show you here? Circuit. So yeah, this is about using differentiations. One reveals the hidden constraints. One finds all these constraints that are necessary for the initial conditions, and what one also can do is one can resolve or replace the constraints. So if you know all constraints, you can either resolve them or replace them by an ODE, and then turn the DAE into an ODE. And yeah, that's what I wanted to show you here. So this is the circuit example. What we can do is differentiate those two equations. So those two equations are going to be differentiated, and then we will have now I put this directly on the other side, minus x dot minus x3 dot u dot minus x3 dot 0, and we had this other equation here. X3 dot minus X2 dot is minus X1 minus X2 over C times R. And if one has a look at these coefficient matrix here, that looks here we have a 1, a minus 1, and a 0. Here we have a minus 1, a 0, and a minus 1. Here we have a 0, 0, minus 1. So this part, if we write this with a matrix, x1, x2, x3, dot on all of that. So can invest another color for that. So all this system here, this could be written with matrix form as this system here, and then it's easy to see that this is an invertible matrix. I hope everyone sees this here. So here's a part which is clearly invertible, and this part is invertible too. So here we have an invertible matrix, meaning we can apply the inverse from this, and then we get, and then all this system will become, this can be written as x dot is equal to some matrix Ax plus F, and this is an ODE. So, and this was an example how one can resolve and replace the constraints in order to turn the DAE into an ODE. This brings me to the last point of today on the index of such equations. It took one differentiation to turn the circuit example into an ODE. Show you this once more. So this was the actual equations. Then we differentiated those two equations. They gave us that, and then we observed that we can invert the matrix that is in front of all these, or that make up the coefficients here. So one can rewrite the system as x dot is ax plus f, and this is an ordinary differential equation. So here it took one differentiation to turn the circuit example into an ODE. This is also possible for the pendulum. For the pendulum, this is possible too, but will take you two differentiations. Like these operations, or the distance of the DAE to the ODE. This can be qualified through the index. This is qualified through the so-called index. And index is an important notion for DAEs, but there's a lot of different theories. We will learn a few theories on that, but maybe as a general rule, low index, this means almost, this is almost an ODE, and high index This is a difficult DAE. DAE. Well, but we learn on that, and with that we will start. No, first we need some more theory in order to show you what is possible with transforming all these DAEs. But once we are there, then we can start talking of the index and do all the steps that I illustrated for you. We can do them in a mathematical, sound and rigid way. Okay, so much for this lecture, and the next lecture will follow soon.